All right, calculus students. Today we're going to be taking a look at the very first lesson that we can really say is worthy of calling at calculus level, and that is a fundamental issue that began back in the early days of calculus and is referred to as the tangent line problem. Okay, so let's take a look. Our objective and essential question for the day. Our objective is to learn to determine the equations of lines that are tangent to, I should say, given curves. Obviously, I've got a bad typo there. Our language objective is to determine slopes of lines that are tangent to given curves and write the equations of those lines. Pardon me. And the essential question, okay, this is the final question that you're answering for yourself at the conclusion of the lesson to determine if you are ready to move on or if you need to spend more time here, is can I determine slopes and equations using the definition of a tangent line? At the conclusion of your practice exercises, if you can handle this, then you can probably move on. If you cannot, then you probably need to spend a little bit more time here. All right. Now, one of the first major problems that earliest calculus mathematicians and people studying physics and things like that, they encountered was called the tangent line problem. Now, in geometry, we already had a definition for what we were considering to be a tangent line, and it was defined geometrically in a circle. So you're probably well familiar with this definition. It looks very similar to this, and the tangent line, of course, it only makes contact with the circle at one point, and it does it in such a way that the tangent is perpendicular to the radius of the circle. Okay, so that was the textbook definition for a tangent at that point in time. Okay, but then the issue quickly arose as we started studying deeper into physics and into calculus. What happens with this definition when you try to apply it to other curves? Well, there are other curves where this works just fine. So the question became, is a geometric tangent going to be equivalent to a calculus tangent, or did the definition need some modification? Okay, now you don't have to think very far. Obviously, the example worked there for the parabola, but when you get more advanced type curves that are doing all kinds of different things, well, we run into the distinct possibility that obviously what we are considering to be a tangent, making contact with the curve in one location and applying to other properties, it did not hold true. We could not say that, oh, that old definition for tangent actually did still apply. Okay, so then the definition evolved somewhat and said, okay, now we want to touch the curve one time, but we do not want to cross it like the example that was above. Okay, so then you go, oh, okay, cool, I see what you got going on there. And then it became, okay, now we've got another issue. If it's a line, as the definition suggests, then as it continues on, it definitely possesses the possibility to run into the curve more than once. So again, they went back to the drawing board and continued to work on the definition. Okay, ultimately, of course, it was Isaac Newton, one of the main fathers of calculus, and he was given credit for defining the idea of localizing a discussion to the point of tangency. So it wasn't necessarily a discussion of the entire line. The line wasn't the focus. It was the point of tangency that was the focus, and that allowed this particular definition to kind of become unlocked. So considering the previous curve, okay, and what we're going to do here is Newton said, okay, what we want the red point and the blue point to coexist. So basically started saying, okay, I want the blue point to basically begin sliding along the curve and continue to approach the red curve, almost similar to the definition of a limit. And once the points coincide, they essentially become one point. Okay, that is the definition of a tangent line, and instead of thinking of it as a line, you basically kind of consider it more as a line segment, because it's only really relevant what's happening right around the point of tangency. So if we kind of disregard the rest of the line, then we're able to move forward. Okay. Now, from this line of reasoning, we get a definition, and at first glance, this is going to seem very, very complicated, but a lot of things in calculus are going to appear that way at first. The key is to not get too spooked about what you see in calculus or what you see on these definitions. Okay. Don't decide whether something is easy or hard by looking at the formula or by looking at the definition. Learn to apply it to particular situations, and then you can make your determinations as to whether you believe something is easy or difficult. Okay, so let's say we're looking at some function f, and f is defined upon an open interval containing some arbitrary value c. Okay, this is where Newton is looking at just the area that is surrounding the point of tangency along the curve. Okay, now here is basically the calculus format for the idea of slope, rise over run. As you can see there, the fraction in the middle, delta y over delta x, that's change in y over change in x. That's rise over run, and as you can see, it is equal to m, which is slope. Now the limit notation there says as delta x goes to 0. Now that's exactly what we saw on the previous slide with the red point and the blue point approaching each other. We are basically causing the distance between that red point and that blue point to become as close to 0 as possible without the ultimately that distance totally vanishing. So there's the idea of the limit. We want delta x to approach 0, get very, very close to it, okay, but not actually reach it, and that's what you're stating. The limit as delta x goes to 0 of delta y over delta x, which of course is slope. And if that limit exists, meaning it's not a vertical situation, we don't have undefined slope, then the line passing through that particular location, which is xy, okay, but the more calculus type notation is to say c, which is some value along your independent axis, your x-axis, and then f of c, which is the function evaluated at your particular location in the x-axis. Okay, it has a slope of m, okay, and that slope is to the tangent line of the graph of the function at the point of tangency, which again is at c comma f of c. Okay, now this is not actually the format we're going to be using. The one you're getting ready to learn how to apply is coming, and here it is. Once again, the limit as delta x goes to 0 of the slope fraction. Okay, the limit is this. Okay, now as this is a formula, we're going to be plugging a lot of information into this formula, but don't let the formula spook you too bad. Let's see if we can understand what it is actually trying to say. Of course, the limit as delta x goes to 0. Again, the denominator, okay, the distance between the red point and the blue point, okay, they are trying to get as close together as possible. So our denominator is trying to vanish. Okay, in the numerator, we have the function evaluated at x plus delta x minus the function itself. Okay, now if you think about that numerator, then what we're looking at is in that numerator the first term, the function evaluated at x plus delta x. Well, what is x plus delta x? Okay, well, f of x, that first term of the binomial, that is simply the function wherever the function happens to be being looked at. Then you have plus delta x. Well, what's delta x? That is the distance between the red point and the blue point. But of course, the red point and the blue point are trying to approach each other. So we are looking at, on that first term, we are looking at the function at the blue point. Okay, and then minus f of x, that is the function at the red point. Okay, so you have a difference in the numerator of where the 2 points are along the curve. That's basically your rise. Okay, so you're still looking at rise over run. It's just a much different format for writing it down. Okay, and that's going to be our slope. Okay, so anytime we want to know the slope of a line that is tangent to a curve, this is the formula that we're going to apply. And this is going to be a very important formula to our work this year, so it's going to be definitely one that we're going to get memorized. Okay. This is, as now, the definition of a tangent line. Okay, so let's take a look at the definition of a tangent line in motion here. Example, find the slope of the graph of f of x equals x squared plus 1 at point 0, 1. Okay, now hopefully just decoding the equation, you ought to be able to look at it and determine that this is a vertically oriented parabola that is traveling upwards, and its vertex has been shifted 1 unit up. Okay, now let's see what happens here. We have a formula. If we want to know what's happening with a particular slope of a particular line at a particular point, that's where our definition of tangent line comes into play. So I've written it down again, and that is absolutely a strategy that I think everybody needs to get into the habit of doing. A lot of times in mathematics, one of our biggest problems is we make the error of trying to plug too much information together mentally before writing anything down. So I would make it a habit to write down your formula so you can have your problem and your formula written in the same place at the same time. The limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, and that is your slope. Okay, now let's see if we can't start figuring this thing out. The formula says in the numerator your function evaluated at x plus delta x. That means in our function, anywhere we find an x value, we're going to take that out and we're going to plug in x plus delta x. From that, we are going to subtract f of x, which is the function itself, x squared plus 1. Okay, so let's make those substitutions. There's what you have. On the left side of the numerator, you have x squared plus 1 being evaluated at x plus delta x. And on the right side of the numerator, we have the function itself, x squared plus 1. Nothing has happened to the denominator yet. The limit is not really in play just yet. Okay, now simplifying the algebra here, we've got a binomial being squared on the left side of the numerator there, and we've got some subtraction going on the right side, so we need to do a little distribution. Okay, so after doing the distribution of the binomial, we have x squared plus 2x delta x, and then we have plus delta x, which is squared, and then doing the we got the plus 1 hanging on to the end of that, and then the distribution on the right side. Okay, we got negative x squared and negative 1, and again the denominator remains unchanged for the moment. Okay, now looking at the problem a little bit, we have some simplification that can be done. We've got some combining like terms. Okay, so combining our like terms, okay, we had an x squared minus an x squared, so those went away. We had a positive 1 and a negative 1, so those went away. And we're left with only the 2x delta x and the delta x squared. Okay, now the next thing you ought to notice there is that all of those terms have a delta x in common. Okay, so if all of those terms have a delta x in common, we can factor it out. When that happens, we actually lose our denominator, which is good. It was trying to go to 0 anyway, so we'd very much like to get rid of that denominator, and now it's gone. And each of the terms in the numerator lost a delta x, so now we have 2x plus delta x. Okay, now there's nothing else that we can simplify here, so it's probably time to go ahead and apply our limit. Okay, delta x, as the limit states, is trying to go to 0. So that is going to take the trail term in that binomial, and it's going to knock it out of the problem. We have basically 2x plus nothing, so that is just 2x. No reason to write down the limit anymore because the limit has already been simplified out. Okay, now what we have here is we have a statement that says what is trying to happen with our slope at a particular location. Okay, so the slope at any point along the function can be used by plugging in this expression. Okay, and we were told to evaluate that particular slope at 0, 1. So what we're going to do is we're going to take the x value out of that coordinate and we're going to plug it into our slope expression. So 2 times 0 is going to be obviously 0. So what's happening with the slope at this particular, or the tangent line at this particular location? It's horizontal. We have 0 slope. Okay, and we can apply this to any particular location. If they had asked about any other point, let's say for example -1 comma 2, that's fine. We simply take the 2x that we've already simplified for using the tangent line definition, and we will plug in our new independent value, -1, and then you have a slope of the tangent line at that particular location. And of course, using the slope value and the particular coordinate you're looking at, you can very simply, very easily write the equation of that line in slope-intercept form using your slope and your point, or write it into point-slope form really very easily. Okay, so anyway, you can kind of see where this is heading. Okay, take a look at one more. Find the equation of the tangent line for f of x equals x squared minus x minus 5, evaluated at -4, 15. Okay. Now, once again, we're going to use the definition of the tangent line. So I would write that formula down until we get that thing absolutely perfect, which will probably be never. But anyway, write it down so we can have all the information in one place at one time, and then start plugging things in. In the numerator, take the function and evaluate it at x plus delta x, and then subtract the function itself. Okay, so plugging in, here's what we have. X squared, so that's x plus delta x squared, minus x, which is minus x plus delta x, and minus 5. From that, we subtract the function itself, x squared minus x minus 5. Okay. The next step is to clean up the numerator. So we're looking for like terms. Actually, not like terms yet. I'm sorry. We've got to deal with that binomial that's in there first. So we're going to expand that binomial and also do some distribution. We got a bunch of subtraction going on in there, so we want to pay close attention to our signs. Okay, there's the expansion of the binomial on the left of the numerator. Okay, and cleaning up the like terms, paying close attention to the distribution. Okay, it should simplify all the way down to 2x delta x. Then we have a delta x squared and a negative delta x. Of course, looking at the terms, we see in the trinomial and the numerator, all of the terms have a delta x that they can forfeit, and the denominator has one as well, so we can cancel those guys out. That leaves us with 2x plus delta x minus 1. And then we've simplified as far as we can, so it's time to send the delta x limit, send it to 0, which will take out the center term, and you're left with 2x minus 1. Okay, so from that particular point, we can, or from this function, we can evaluate the slope of any line by plugging in where on the line you actually want to look at. In this case, we were told to look at -4, 15. So we're going to take x out of our slope expression of our tangent line and replace it with -4 and simplify, and we have a slope of -9 at that particular location. Okay, and as I said, if you need the equation, you can finish this off by plugging in your slope value in any coordinate on the line. Typically, I do this by slope-intercept form. It's just the format that we have had the most exposure to over the years, so it's the one that I tend to use when I do have a coordinate and a slope. So plugging in the values that I know, we've got 15 equals -9 times -4. And of course, that's 36 on the right. And when we isolate the b, we've got a slope-intercept way down on the y-axis at -21. And now you have all the information you need to assemble your line. The slope of the line that is tangent to the curve at -4, 15 is y equals -9 minus 21. Okay, there's one other example that we're going to do together in class. Okay, so if you are viewing this video ahead of time, copy it down, give it a try. Let's see if you can't figure it out, and we will cover it in class together. Okay. The assignment that goes along with this particular lesson is on page 103, and the assignment is questions number 1 and 2, and then you have 25 through 30 doing only the instructions for part A for each of those 6 questions that are there, and that will be it. We're going to be doing a little bit of jumping around. Some of chapter 1 is a little redundant. I don't think we need to spend all of our time doing all of the chapter 1 stuff, so this is actually the first section into chapter 2, which is why we're way into page 103 all of a sudden. But anyway, I trust we'll get to where we need to go, get to by the time we need to get there. So just trust me while we skip around a little bit, and that's good. I'll see you in class.